A robot video goes viral because the motion looks human, but on Titan's equator, that same machine would simply vanish into a mechanical trap. Standard rovers fail here not because of the crushing cold or radiation, but because the ground itself is an alien paradox. While Earth robots rely on wheels gripping sand or rock, Titan features dunes made of water ice grains coated in slippery hydrocarbons, essentially frozen, oily marbles that shift under sudden methane storms. The engineering nightmare isn't just survival, it's traction and control. A standard wheel design will sink, slip, or get stuck instantly on this ice-oil mixture, while the winds themselves blow contrary to climate models, hitting robots with unexpected eastward gusts rather than steady breezes. This brief analyzes why Earth-based locomotion physics break down at 94 Kelvin and what new mechanical architectures are required for autonomy in this unique environment. The first hurdle is understanding the substrate paradox that makes Titan so unforgiving for terrestrial designs. The equatorial dunes consist of water ice grains coated in hydrocarbon deposits that fell from the Moon's orange atmosphere over millions of years. This creates a surface with low friction and high cohesion, behaving nothing like Earth sand or even Mars regolith. Standard rigid wheels designed for granular soil lose traction on this oily ice mixture, leading to slippage rather than forward motion. It is akin to trying to drive a car on a floor covered in frozen soap bubbles. The tires spin uselessly while the surface yields and shifts beneath them. This mechanical instability is compounded by a wind contradiction that caught planetary scientists off guard until recently. A landmark study published in Nature Geoscience in April of 2015 revealed that Titan's massive dunes are shaped by eastward winds, directly contradicting the westward trade winds predicted by standard global climate models. These dunes form during rare but violent methane storms driven by high-altitude atmospheric superrotation. Robots must be engineered to withstand sudden, powerful gust fronts capable of moving heavy ice grains in unexpected directions, rather than just slow surface breezes that a rover might simply plow through on Earth. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. When you combine this slippery substrate with the specific gravity and atmosphere density, conventional rovers face what we can call a locomotion black hole. On Titan's low-gravity environment, which is only 14% of Earth's, combined with its dense atmosphere and loose hydrocarbon-coated ice, standard traction physics simply fail. A machine like Curiosity or Perseverance would likely sink deep into the dunes or be pushed sideways by a storm it wasn't designed to resist. The rigid chassis that works well on rocky Mars becomes a liability here, as there is no solid footing to leverage against for movement. To bypass these bottlenecks, engineers are proposing two distinct mechanical approaches that abandon traditional wheels entirely. The first concept comes from NASA Ames researchers who proposed the Superball bot in 2013. This design replaces rigid wheels with a deformable spherical exoskeleton. Instead of trying to force traction through rotation, the robot absorbs landing shock without airbags and can squish over dunes. By deforming its shape, it maintains contact on slippery ice rather than rolling off or sinking, effectively adapting its geometry to the unstable ground in real time. The second approach looks toward soft morphing aerials that utilize Titan's dense atmosphere for lift while avoiding wheels altogether. Researchers at the University of Seville have proposed drones using Teflon with specific infill rates designed for thermal stability in cryogenic temperatures. These robots use flexible arms to perch on irregular dunes and transition into continuum manipulators, navigating tight spaces via rotor tilting rather than body rotation. This aerial strategy highlights a crucial realization about Titan exploration. Flying is often mechanically simpler than walking because the dense air provides buoyancy that rigid-wheeled rovers cannot match against shifting ice sands. This shift in design philosophy reveals why one-size-fits-all robotics fails when you leave Earth. Viewers often assume space robots are just ruggedized versions of their car or vacuum cleaner, but Titan proves that alien environments require fundamentally different mechanical intelligence. The takeaway is the hidden trade-off. To move on Titan, engineers must abandon rigid wheels for soft materials and aerial autonomy because the physics of grip simply do not exist there in a traditional sense. This explains why NASA's Dragonfly mission chose an octocopter over a rover. It isn't just about speed or range. but that flying is often mechanically superior when traction is non-existent. The future of extraterrestrial exploration on bodies like Titan is not about making Earth robots tougher by adding more power or better grip tape. It is about designing machines that think in 3 dimensions and move with soft materials rather than rigid levers. The engineering reality behind what these systems can actually do requires us to accept that the most efficient way to explore a dune field on another moon might be to leave it entirely, floating above the very ground that would trap any wheeled vehicle sent below. We are standing at the edge of understanding how mechanical intelligence must adapt when the physical laws of movement change completely. The contrast between Earth's solid grip and Titan's slippery chaos forces a re-evaluation of what autonomy means for exploration machines. As we push further into our solar system, the most successful robots will be those that can deform, fly, or float, rather than simply drive over surfaces they were not designed to conquer. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.